Hello, my name is Dr. Kevin Wackett. I am a postdoctoral researcher in the Zaban group at Bar-Ilan University. This video is the first in a short series of videos to be presented by myself to provide a glimpse in the research facilities and activities of the Zaban group. The group investigates sustainable electrical energy in the form of solar energy conversion and storage. One of the main research goals is the development of all-oxide photovoltaics, namely solar cells fabricated from metal oxide materials. With continually growing energy requirements and dwindling fossil fuels, it is necessary to promote low-cost renewable energy production, and solar energy is the most promising method. In order to lower the cost of photovoltaic modules, it is necessary to discover new, inexpensive raw materials that can be used to produce cells cheaper than contemporary silicon cells. While many different types of materials are being investigated worldwide, we believe the answer lies in metal oxides, a class of materials with a wide variety of physical properties, from electrically insulating to superconductivity. They are stable, non-toxic, abundant, and have been employed in a wide range of important applications, including microelectronics, nanoelectronics, photocatalysis, and thin film electronics.
Metal oxide compounds are comprised of oxygen and one or more metal elements. They are readily alloyed together, which allows the fine-tuning of select desirable qualities such as high light absorption and electrical conductivity. This quality has been greatly exploited in high-temperature superconductivity, since the critical temperature, which is a key figure of merit for superconductive materials, has been steadily increased over the past 3 decades by incrementally increasing the complexity of metal oxide compounds used. Given the number of suitable metal elements, there are thousands of possible combinations, and it is very likely that with sufficient understanding, it is possible to engineer materials with very select sets of properties for any desirable application. Insights into metal oxide compounds, it is necessary to employ a high throughput approach, and here in the Zaban lab we use a combinatorial materials cycle. One of our main activities is to mix metal oxides and to test their performance as absorber layers in solar cells. To fabricate our cells, we start with a glass substrate with a 200 nanometer thick fluorine-doped tin oxide layer, which is used as a transparent contact, onto which we deposit a transparent N-type TiO2 layer. A metal oxide compound is synthesized on top of this layer and acts as a light-absorbing material and forms a p-n junction with the TiO2, resulting in an internal electric field that is used to separate the charge carriers and form a photocurrent. This is the active layer, and is grown with a controlled spatial gradient in the chemical composition and or thickness over an area of 7 cm by 7 cm. Due to the spatial gradient in the metal oxide compounds, each cell is unique. The absorber layer in this example was grown with cupric or copper oxide at the top, and the co-deposition of magnesia or magnesium oxide at the bottom. In order to analyze a large number of metal oxide combinations, libraries are rapidly characterized using a series of automated scanning robots to perform analytical measurements in an array of points across the sample. The Zaban group currently has 12 scanning instruments that are routinely used. Each scanner utilizes a local area measurement that is performed sequentially in an array of predefined positions across the library, which allows direct comparison between all the results. For example, we have the optical scanner, the resistivity scanner, and an IV scanner. The experimental data that is collected from each of these scanners is curated with the relevant metadata and stored in a database. This data is analyzed for each library individually using conventional modeling and or informatics to identify trends in the material properties with respect to the processing parameters and or other properties. My particular focus in this project is to understand how the electronic properties of metal oxide compounds can be tuned through mixing, and to investigate energy level alignment and metal oxide interfaces. A scanning Kelvin probe apparatus will be utilized to map the contact potential difference and subsequently the work function of the sample. An oscillating tip is brought close to the sample to form a dynamic parallel plate capacitor. The controlled variation in the separation of the tip from the sample leads to a varying capacitance and induces an AC current that is measured and used to determine the work function of our material. Our Kelvin probe has an additional module that shines a monochromated UV light onto the sample, sweeps the energy of the light, and measures the photocurrent that flows between the tip and the sample. The measurements are based on the photoelectric effect and determines the ionization energy of the sample by measuring at what energy the photocurrent starts to flow, which corresponds to the ionization energy of the sample. Lastly, a custom inbuilt UV-vis optical scanner, which was shown earlier, will be used to measure the total transmission, total reflection, and spectral reflection of light over a wide range of wavelengths, from 400 to 1000 nanometers. From these measurements, we will develop talc plots and determine the band gap of our material. So to briefly summarize, Kelvin probe will provide us with a work function. The air photo emission system will provide us with the ionization energy, and using optical measurements we will determine the band gap. Together we can ascertain an entire band diagram. A band diagram is a convenient way to summarize the electronic properties of a material, and it's been the bread and butter of the semiconductor industry for decades. To highlight the abilities to tune the electronic properties of metal oxide compounds with a spatial variation in the chemical composition, and to demonstrate our analytical capabilities, we return to the copper-magnesia oxide sample that was described earlier, in which the cuprous oxide was grown at the top and the magnesia oxide at the bottom. From energy dispersive X-ray spectroscopy, we obtain the chemical composition mass, and can see that the copper is rich at the top and the magnesium is rich at the bottom, as expected. The corresponding work function, ionization energy, and band gap mass for this compound are also shown. From this information, local band diagrams can be drawn at each point of the maps to provide a useful and transferable summary of the electronic properties, as demonstrated for two distinct chemical compositions, indicated here by the black and the grey circles. The black one shown on the left, the grey band diagram shown on the right. Two things are of particular interest. The left band diagram has a band gap of 1.4 eV, which is considered ideal for the light absorbing layer in solar cells, as it provides a balance of the number of photons that can be captured and the energy of these photons. The other thing worth noting is that this band gap is not unique to this specific composition or position on the sample. Other compositions demonstrate a similar band gap, but with different work functions and ionization energies. This allows one to have the ideal band gap, but with control over the specific values of the other qualities, which can greatly impact on the performance of the resulting solar cell made from this material. Having described how we characterize the electronic properties of a single material, we can now characterize metal oxide junctions. In order to minimize the total charge of the system, electrons flow from the material with a lesser work function to the one with a higher work function, lowering the Fermi energy in the former and raising it in the latter, until the Fermi levels align and thermal equilibrium is established. This transfer of charge results in a spatially varying electric field observed as band bending in the vicinity of the interface. The simplest example of this is the p-n junction that has been shown. Band bending can occur over the lengths of a few nanometers up to hundreds of nanometers from the interface, and therefore can play a significant role in the operation of many devices, and is key for the operation of solar cells. For this reason, we have devised a novel method to determine the energetics of such a junction. We will map out the variation of energetics throughout the junction by first measuring one metal oxide material and growing a second layer on top. The second layer will have a thickness gradient. We will scan across the gradient of the second oxide layer and at each point measure the relevant properties such as the work function and ionization energy, and correlate these values with the thickness of the add layer. By reversing the order of the metal oxide compounds, we can then develop a full understanding of both sides of the junction. This is a powerful analytical technique for characterizing junctions, and with it we can measure the energetics of entire solar cells and establish a deep insight into the electronic properties of complete devices.
With such advanced high-throughput scanning instruments in the Zaban group, the research possibilities are endless. If you'd like to learn more, you can visit the Zaban Lab website to view our publications, our presentations, to obtain contact details, or to follow this series of videos. Thank you very much for watching.